Okay, good evening, everybody. And welcome to another session of organic chemistry. In today's session, we are going to start our discussion on the chemistry of alkynes, which you will find on in chapter 9 of your text. You will find that the chemistry of alkynes, most of what we did in the chemistry of alkenes, we are going to use a lot of the same reagents that we use in the chemistry of alkenes. So most of these reactions in this chapter should be familiar to all of you. Of course, we are going to start with the nomenclature. Then we get to the synthesis of alkynes. And then we finish up on the with the reactions of alkynes. Okay, on this slide you have a list of learning outcome objectives. These are the list of concepts and topics that you should be familiar with and you should master during the course of studying this particular chapter. Okay, of course, the first question that comes to mind is, what are alkynes? As you can see, alkynes are those organic molecules that contain carbon-carbon triple bond. Okay, but before we get to the nomenclature of alkynes, let us take a few minutes to discuss the orbital picture of alkynes. Okay, we say alkynes are those organic molecules that contain the carbon-carbon triple bond, and the simplest alkyne is this molecule here, which we call acetylene. As you can see in this molecule, you have this carbon-carbon triple bond. And each one of these carbon here is an it's an sp hybridized carbon. This is an sp carbon, and this is an sp carbon. We also know that we have two pi bonds in this molecule. Okay, pi bond, and a sigma bond right here between the carbon-carbon triple bond. So we may want to take a closer look at this orbital picture of this molecule. For example, we have the carbon. One carbon is bonded to hydrogen using a sigma bond. Another carbon is bonded to the other carbon using a sigma bond. And the second carbon is bonded to another hydrogen atom using sigma. So all of these are sigma bonds. And then on each one of the carbon atoms, because this carbon here is an sp carbon atom, you have two p orbitals. So you have two p orbitals on each one of the carbon atoms, and each one of the p orbitals, of course, contain one electron. The same thing on this carbon here. also containing 1 electron each. And then you now have, because we know that carbon is tetravalent, carbon needs 4 bonds, you are going to get overlap of p orbitals. You could imagine that this p orbital here will overlap with this, and this other p orbital will overlap. Each one of these overlap of p orbital here will constitute your pi bond. So this will be your pi bond right here, and this is another pi bond right here, and of course these are your sigma bonds. Now, because the carbon-carbon triple bond is rich in electron, we are going to expect that a lot of the reactions that we encounter in the alkene molecules, we are going to encounter the same type of reactions with respect to the carbon-carbon triple bond. Even more so, they will be even more reactive because of the richness of electron in the carbon-carbon triple bond system. Now let us begin to take a look at the nomenclature of alkynes. Oh, by the way, I do also want to let you know before we get to nomenclature that this bond angle here between this carbon hydrogen and this carbon here, the bond angle is 180 degrees. The same thing here. In other words, this is a linear molecule. Okay, and that will impact on the chemistry of these molecules. Okay, so now let us begin to take a look at the nomenclature of alkynes. For the nomenclature, the name of the alkyne is derived from the name of the corresponding alkane molecule, just as in the case of the alkenes. For example, the simplest alkyne, which is acetylene, that is the common name, acetylene, the corresponding alkane will be this molecule here. And the name of the corresponding alkane, of course, will be ethane. This here is ethane. So what do we do to name the alkyne? We remove the last A and E of the alkane name, and we replace with Y and E. So therefore, the Y and E, this is the suffix for alkyne. In other words, that is the ending for alkyne. So therefore, how do we name this? Given that information, how do we name acetylene? What would be the IUPAC name for acetylene? Ethyne, very good. So this becomes ethyne. Okay, and that would be the IUPAC name for that molecule. Even though the common name is actually more in use because it has been around for so long. Okay, so the IUPAC name will be ethyne. Now let us look at some more examples. Supposing we have this. What would be the name of that alkyne? What will be the name? In this case, propine, right? Okay, you don't need to indicate the number here because really it doesn't. There's no need for it at this point. So this will be propine. How about this here? How about that? What would be the name of that? What kind of butane? 1-butane, very good. Which one?
You said we have to put one because there's only one supervisor here anyway.
In the propine?
Like both of them. Like you put it in the use time, but you didn't put it in proton.
Yeah, because there is no need for it. Whatever it is going to be 1 anyway. There is no other possibility for profile. Okay, for example, what if I have this? What would be the name of that molecule? What is it? 2-butane, exactly. Okay? How about that molecule? What is it? 3 hexane, exactly. Now let us look at a little bit more complexity here. Supposing we increase the complexity of this molecule, now we begin to place branches on them or substituents on them. Okay, in this instance, you have to assign the lowest possible number to the carbon-carbon triple bond, okay? So you have to assign the lowest possible number to the carbon-carbon triple bond. And then after you do that, the substituents will then be assigned the appropriate numbers. So what will be the numbering here? Do we start numbering from here? Let us say this is left and this is right. Do you start numbering from the right or from the left? From the left? Okay, very good. So that is 1, 2, 3, 4, 5, 6, 7, and 8. So what are we going to call this molecule? What is it? 6-methyl, very good. 6-methyl and 3-octane, very good. Now supposing we have this, what are we going to call this? Now we have multiple triple bonds. Where do we start the numbering? From the left or from the right? From the left, okay? Because you want to assign the lowest possible number to the multiple bonds. Okay. So this becomes 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the base name for this will be from decane. Okay, very good. So therefore, what will be the name for this? 6. Oh no, I'm sorry, 8. 8 methyl. Okay. 8 methyl 2, 4, 6, right? Okay. 8 methyl 2, 4, 2, 4, 6. Deca, right? Deca, just like in the case of the alkenes, tri-ene. Okay? Keep in mind you have the suffix is still right there. Tri-ene. So you have 3 of them. If you have 4, you have tetra. If you have 5, penta. Okay. Now supposing we have a molecule that contains a double bond and a triple bond. Supposing we have a molecule that contains a double bond and a triple bond. Okay? If you have a molecule that contains a double bond and a triple bond, the double bond takes preference. Okay? At this point, the double bond will take preference. You are going to name this as an alkene. Now, in terms of the numbering, you have to also number to give the multiple bonds the lowest possible number. Okay? In this case, it just so happens that it does not matter. You could start from here or here. It should be 1 or 1. In that case, you have to give the preference to the carbon-carbon double bond. Okay? Carbon-carbon double bond takes the preference. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, now to name this. Okay, this would be octane, 1 octane, right? Say 1 octane. Now to indicate the position of the triple bond, what you do, you remove the E ending of the alkene. There's an alkene here. And then you indicate the position of the triple bond. 7 becomes 7 in. 1 octane, 7 in. Because in this case, the carbon-carbon triple bond is also on the 7th carbon, right here. Now, if you have some other branches here, supposing you have a branch here, you still have to follow the same rules that we have been following in terms of alphabetizing. You have chlorine here, for example, and let us say we have here let's say we have a methyl here. Okay, so now this becomes, what would be the name? 4-chloro, alphabetized in order. 4-chloro. Okay, very good. 4-chloro, 6-methyl. Then you have to indicate the position of the carbon-carbon double bond. 1 octane. 1 octane, 7 in. Okay, supposing we have this. Okay. How do we name this? Let me do this better than this. Okay. In this case, we have 2 carbon-carbon triple bond and 1 carbon-carbon double bond, right? How would you name this? Keep in mind you have to start numbering so that you give the multiple bonds the lowest combination of numbers. Okay, where do we start to number? From the left or right? Left? Oh, I didn't do that on purpose. Everything has been left. I didn't mean to do that, but anyway. So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the base name will be octane, right? Okay. Now let us now what to be the name? The scene, right? Because we have to name this as an alkene, and the alkene is in what position? The double bond is in what position? 4. Okay. So we say this is 4. The scene. Okay, hyphen, the triple bond in what position? 2 and 7, right? You have 2, 7, die in. Okay, so I'm going to leave the rest of the nomenclature for you guys to take a look at your text and do all of the problem in the back of your book. They do have some excellent problem set in the back of your book, so I'm going to leave that to you. So now let us begin to take a look at the synthesis of alkyne. Oh, yeah, but yes.
So when you say iron and heme, they don't sound the same when you say, because you make it sound like heme and iron are the same.
Well, maybe that's all. It should be iron. It should be iron. It should be iron. Just like alkyne. Yeah. Oh, okay. I see what you mean. It sounds like E-N-E. Yeah, it's iron. Okay, it's iron. It should be iron. Okay. One more thing I need to tell you. Because of the geometry of the alkyne, because the bond angle is 180 degrees between this carbon and this carbon and this hydrogen and this carbon here. Bond angle is 180 degrees. Because of that, you cannot have an alkyne in a small ring system. Okay? For example, you cannot have an alkyne in a molecule like this. That's not possible. Because of there will be too much bond strain, and that will not be possible. But however, if you have a bigger cyclic molecule with at least about 8 carbon atoms, somewhere between 8 to above 8 carbon atoms, then you can begin to have the shape of the molecule that will allow for that kind of bond angle, 180 degrees. For example, you could have this. So you could have a cyclic alkyne as long as you have more than 8 carbon atoms in that molecule, because the shape is such that to allow you to have a bond angle of 180 degrees here, and another 180 degrees here. Okay. However, small cyclic molecule, you cannot have an alkyne because of the bond strain. Okay. Okay, now let us begin to take a look at the synthesis of alkynes. Actually, it's only one of them, one synthesis of alkyne that we use in the laboratory. And that you're already familiar with. You say that is dehydrohalogenation. Dehydrohalogenation. Okay, which simply means elimination of hydrogen and halogen. That's what dehydrohalogenation means. If, for example, we have this, say we have that model. And we use this reagent here, potassium hydroxide. Generally, when we use potassium hydroxide, we very often use this ethanol as solvent. Ethanol as solvent. What this will do is to remove 2 molecules of hydrogen bromide from here. Actually, you have 2 dehydrohalogenation taking place. And so you are going to get this. So to get that, we get KBr and water. So you have 2 dehydrohalogenation taking place. Instead of using potassium hydroxide, we could also use this other molecule here, or this other reagent here, this here, called sodium amide. Very often when we use sodium amide, we also use this in the presence of ammonia as solvent. So you could see us write sodium amide with ammonia, or sometimes sodium amide by itself. The same thing we do here, we could simply just write potassium hydroxide. Okay? The net process is the elimination of 2 bromine atoms and 2 hydrogen atoms. If you recall, we use the same process for the synthesis of alkene. In that case, we only did 1 dehydrohalogenation. Okay? So this reagent here, that is what this will do. If therefore, if I do this, supposing I do this, and I say, give me the product of that reaction, what will it be? What will be the product of that reaction? What is it? What will be, yes, going to form an alkyne, right? That's dehydrohalogenation. Okay, in other words, we are going to remove the bromine and hydrogen on these 2 carbons here. So therefore, we have this. Okay. And that would be 1 hexyne. Or we could use sodium amide. Okay, that is the only synthesis of alkyne we are going to give you. Now let us go to the reactions of alkyne. Yes. Finish? Okay. Now, for the reactions of alkynes, as you already know, just as in the case of the alkenes, there are a lot of reactions. So what I'm going to make it easy for you, I will number them. Some of the reagents you already have, should be familiar to you. Okay, so let us start with 1, hydrogenation. Hydrogenation. Hydrogenation simply means we are adding hydrogen, 2 hydrogen atoms, or hydrogen atoms across the carbon-carbon triple bond. Okay, so this is addition of hydrogens. Okay. Across carbon-carbon triple bond. There are 3 types of hydrogenation I'm going to introduce to you. So let's just call this 1A. A, catalytic hydrogenation. Catalytic hydrogenation using metal catalyst. Such as palladium, platinum. Sometimes we use palladium on carbon, PD on carbon. Sometimes we use platinum oxide. This palladium on carbon. So these are the various types of metal catalysts that we could use in hydrogenation, catalytic hydrogenation. A few examples. If I have this, and I do this, hydrogen, palladium over carbon, what this will do is to completely convert this carbon-carbon triple bond, these sp carbons here, into sp3 carbons. You notice what I've done here? According to this equation here, you will say, well, you only have 1 mole of 1 equivalent of hydrogen. It is very difficult to stop this reaction by simply just adding 1 mole of hydrogen to this to form an alkane. However, if that is what we wanted to do, we will tell you that we are going to use 1 equivalent of hydrogen. Okay? If, for example, I tell you this here, I use 1 equivalent, this 1 equivalent of hydrogen, okay, and then of course the catalyst is here. What I'm trying to tell you here is that you are going to form an alkane, okay? In other words, only one mole will react to form an alkene. But that is very difficult. But if that is what we wanted to do, we will tell you exactly. But if I do not tell you that, or your book does not tell you that, what you have to assume is all of those, the triple bond is completely gone, the double bond is gone, and you now have an sp3 carbons, yes.
You add the molecules to react the alkynes into alkanes and just bonds to the alkanes.
No, if I just tell you that compound A, if I say compound A reacts with hydrogen, in the presence of a catalyst to give compound B, assume that all of the multiple bonds are gone. Okay. But if I tell you that compound A reacts with only one equivalent, what that could be telling you is that you only have one double bond in there, or that we converted the double bond to the triple bond to a double bond. Okay. Okay. Anyway, so if we want to limit what you have to do, we will tell you that a certain number of equivalent of hydrogen is added. Okay. Okay. So that was 1A. Okay. Let us look at B. Okay, I said this will be hydrogenation using lithium or sodium in ammonia to give trans-alkene, This is a very stereospecific reaction. It's stereospecific. You know that only one isomer is formed. If I have this, for example, and I take this here, sodium dissolved in ammonia, or lithium dissolved in ammonia. What this reagent will do is to add two hydrogen atoms across the carbon-carbon triple bond such that those two hydrogen will be trans to each other. We are going to form only alkenes. Okay? This is very important. This is a very important reagent because you do not have too many reagents that will do this. So when you are putting together your list of reagents, this should be one of those you should include in your list of reagents. Indeed, all of these reagents you should include in your list of reagents. Okay, what this does, it turn an alkyne to an alkene, a trans-alkene. That's what it does. Okay, 1C. Hydrogenation using linear catalyst to give cis-alkene. Huh? Lindlar catalyst. With 6 alkane. Okay, Lindlar catalyst is this here. It's hydrogen mixed with calcium carbonate, palladium, and this molecule here called quinoline. So for you, you don't need to write all of this every time you use this. Just write Lindlar catalyst, that's all. Okay, but this is the combination. Okay, so therefore, if I give you that same molecule that we used in the last reaction with the lithium and ammonia, the same starting material, and I use Lindlar, what do I expect to get? 6 alkane. Okay. This is also a stereospecific reaction. Okay, so far I have given you 3 methods for hydrogenation. The first one, which is just the regular catalytic hydrogenation, that simply reduces the alkyne to alkane. But the second one, the lithium and ammonia, or sodium and ammonia, what it does is to reduce or transform the alkyne to alkene, to transalkene. And then the third one, which is this one here, will transform the alkyne to a cis-alkane. Okay. Okay, so now let us take a look at another. That is 1, but 2, reaction 2. Hydrohalogenation. This we also did with the alkene. Hydrohalogenation. And what is that? What does that mean? That means we are adding hydrogen and halogen. Addition of hydrogen and halogen to the carbon-carbon triple bond. Take this. Say we take hydrogen bromide. Okay. Well, let me make this. Let us use a symmetrical molecule here. Okay. Take hydrogen bromide. Okay, what are you going to do? We are going to add hydrogen and bromine across the carbon-carbon double bond. This reaction is also very difficult to control. Very often you go all the way, in which you are going to be adding 2 moles of hydrogen bromide. This will continue. Once you start this reaction, it is very difficult to control where you get only the alkene. So you end up getting sorry about that. Because this is a mechanical addition at this point. So once you add the first molecule of hydrogen bromide, okay, then you are going to add the second molecule of hydrogen bromide. At this point, this is a mechanical addition. And what do we obtain? We obtain what we call a gem dihalide. Now, gem dihalide simply means you have the halogen, in this case the bromine, attached to the same carbon atom. Okay, in this case right here. So this is an example of a gem dihalide. Okay, so that is the addition of hydrogen and halogen across the carbon-carbon triple bond. By the way, all of these reactions that I've given you, you could also perform this using hydrogen chloride. So let us give you one example of that, so you don't think it's only hydrogen bromide. Okay. You also form a gem dichloride.
Don't go straight to the gem chloride when you're giving 2HCl, 2HBr. Otherwise, you have to show all three steps.
No, you don't have to show this. No, if I just give you this, say, give me this.
That's the only time I'm going to show.
Say that again.
So the only time you have to go straight from A to B is when you give 2HCl, so like in the left.
Yes. If I just gave you one, then okay. Okay. So that is reaction number 2 and number 3. Halogenation. This also we did with the alkenes. Halogenation, that is addition of halogens across the carbon-carbon triple bond. And by halogen, we essentially mean they are chlorine and bromine. Yeah, bromine. Okay, don't forget, very often we use a solvent for this, either this dichloromethane or carbon tetrachloride. So if you see that, these are just solvents. Okay, the most important reagent here is this here. Okay, so bromine will react with the carbon-carbon triple bond. just as it does with the carbon-carbon double bond, to add 2 bromine atoms across the carbon-carbon triple bond. And this will be trans addition. So you get a trans product. Now, if you add another mole of bromine, then you get another addition, because at this point, this will be acting as a carbon-carbon double bond. So now you get a tetra-substituted compound. Now we have this. So we could stop this reaction by simply adding 1 mole of bromine from the dibromoalkene, or you may want to continue to go all the way to tetra bromoalkane. Yes. Oh, this here. Well, by doing this, you already show that by having this here, you already show that they are trans, because they are on opposite side of the ring. Yeah. Wedge and dotted line depends on how you're looking at the molecule. Right now, I am looking at the molecule this way. That's the way you're looking at it now. That's why it's flat. But if you look in here, then you see the wedge, one is coming at you. So it depends on your own perspective. Mm-hmm.
You don't need to do H264 in a second.
No, you don't. Very often we don't even write the solvent in there. But I just want to let you know, if you see that anywhere, know that that's just a solvent. Okay. Okay, so that's our reaction number 3, halogenation. Now let us now begin to take a look at hydration. What is hydration? Adding water, exactly. Adding water. That would be 4. Okay. This addition of water so there are 2 types of hydration that I want to show you here. Let's call this 4A. Hydration using mercury 2 salt in acid to give ketones or methyl ketones. To give ketones or methyl ketones. Or methyl ketones. Now, what do I mean by that? If you have this, this is what we call a terminal alkyne. In other words, the carbon-carbon triple bond is at the end of a carbon chain. And we do this, and that reagent will be mercury sulfate, or sometimes you will simply see us write mercury ion, mercury 2 ion, in sulfuric acid, or sometimes instead of writing sulfuric acid, we may simply just write hydronium ion. Okay? That reagent, what does it do? We transform a terminal alkyne to a methyl ketone. Huh? This here.
Yeah.
Mercury sulfate. This is mercury sulfate. Mercury sulfate in the presence of sulfuric acid or in the presence of any dilute acid. And we could indicate the dilute acid by writing hydronium ion. Okay, what that would do is to transform a terminal alkyne to a methyl ketone. In other words, this carbon here becomes a carbonyl of a ketone, and this carbon here becomes a methyl group. Keep in mind, at this point, our focus is on the carbon-carbon triple bond. Okay. On the other hand, if you have an internal alkyne, in other words, the alkyne is within the chain, carbon chain, and you have mercury sulfate in dilute acid. Any one of these carbon here could become the carbonyl carbon. Okay? In the case of an internal alkyne, any one of the carbon-carbon triple bond could become the carbonyl of a ketone. So therefore, what happened here, okay, this one becomes the carbonyl of a ketone, and this one you add 2 hydrogen atoms to this. So the next process is addition of water, okay. Yeah. Or this could also become the carbonyl of a ketone, and this you add the hydrogen to this here. Because in this case we are dealing with a symmetrical molecule. Now if the molecule is not symmetrical, then you are going to get a mixture. You'll be getting a mixture.
Can you repeat all of that?
Okay. Okay, let's give you another example. Supposing if we have this, the last molecule I gave you, that was a symmetrical molecule, right? Supposing I have this. And then I have this. Okay? Now you are going to get 2 products. To get this here, so is that what I want? Okay, no, that's not what I wanted to give you. And you get this. Okay, what I really want to give, okay, you are going to get this, this here. Now, supposing the carbonyl comes here. Okay, in this case, the carbonyl, then let us number this. Say this is 1, 2, 3, 4, and 5, right? Okay, this product I've given you here, the carbonyl comes to the carbon number 3. Supposing the carbonyl comes to carbon number 2, what do you get? You get this. In this case, you get a mixture of products because you are starting with a non-symmetrical alkyne. Now, okay, that was hydration. One, I said there are 2 hydration. Okay, that was 1A. 1B, still under hydration. Yes.
For the example you just gave, you have to write both products?
Yes, if I then you have to write both products. Yes. Okay. Now, was that 4B?
That was, yeah.
This is 4B, right? That was okay. This is 4B. Okay, hydration. Using hydroboration oxidation, we know that already, right? Hydroboration oxidation to give ketones and of ketone or aldehyde, depending on the alkyne that you are starting with. Ketone or aldehyde. If we start with this, and of course we take borane, and you follow that up with hydrogen peroxide in base. Okay. So this reaction will be similar to the last reaction, in which you are going to form a ketone. I know all of you are asking, since you say we are adding water, how are we getting ketone? I will show you that later. Maybe on Thursday, I will give you what is happening in that particular sequence of reaction for us to get a ketone. Okay, but for now, just accept the fact that when you have this here, you are going to convert the carbon-carbon triple bond to either a ketone or aldehyde. So here we have now, supposing we have, okay, in the case of an internal alkyne, which is what this is, we get a ketone. Supposing we have a terminal alkyne, then we get an aldehyde. So what we get depends on our starting material. So in this case, this carbon here, this last carbon here becomes the carbonyl of an aldehyde. becomes the carbonyl of an aldehyde. I said this here becomes the carbonyl of an aldehyde. Okay? Okay? But if you have an internal alkyne, which is what you have here, okay, you are going to get the carbonyl of ketone. Okay, moving right along. Okay, reaction number 5. Oxidative cleavage. I'm sure you heard that before, right? I told you most of these reactions should be familiar to all of you. Oxidative cleavage. To give, this time we get carbon dioxide, carboxylic acid, or carbon dioxide, carboxylic acid, and I would say and or carbon dioxide, depending on what you are starting with. This here if I take potassium permanganate, of course in dilute acid, or ozonolysis, at this point they do the same thing, or step 1 ozone, step 2 then you have the hydrogen peroxide, okay, what do you have here? You get okay, so this part of the molecule here, you can see here, that is this right here. And then this other part, in other words, this will cleave the carbon-carbon triple bond. So you are now going to get 2 carboxylic acid. You get 2 carboxylic acid. Okay? And this part of the molecule right here, and that is this right here. Okay, so what this reagent will do is to cleave the carbon-carbon triple bond so that you get carboxylic acid. Now, if you have a terminal alkyne, you will get a combination of carboxylic acid and carbon dioxide. For example, let us take a look at this here. Let us take a look at that. Okay. Based on what you know now, supposing I give you this molecule here, and I want to do ozonolysis of potassium permanganate, what do you think the product will be? Or you could do the same reaction with ozonolysis, or okay, what would be the product? Okay, let me give you some hint here. Don't forget that this here will cleave a carbon-carbon double bond, right? Yeah. Right? To form a ketone here, right? It will also cleave this to form carbon dioxide here and carboxylic acid, sodium. we should expect to get this. The same thing will happen if you use ozonolysis.
Yeah.
Okay? And then this here, plus carbon dioxide. You see that? Let us number this. Let us say this is 1. Okay? Carbon 2, carbon 3, carbon 4, carbon 5, 6, 7, 8, and 9. Okay? Okay, right now this is carbon 9 right here. This is 8, carbon 8. Of course, this is 7. This is 6. This is 5. This is 4. And this is carbon 3. And this will be your carbon 2. And carbon 1 is your carbon dioxide right there. Okay? Now, of all the reactions I've given you so far, the most, one of what we consider the most important reaction is what we are going to do now. Okay, everybody's got this? Okay. Yes. It's a product?
Like how carbon dioxide is a product of the assessment. Why is it not?
Or why is it not the product of this here? Because keep in mind we told you that if you have a terminal alkyne, the last carbon becomes carbon dioxide. Okay. Just as in the case of a carbon-carbon double bond. Okay. Okay. Now let me, okay, that is 6. Okay, now I'm going to call this. Oh, that was 5, rather. This is 6. Reactions of acetylide ions. Reactions of acetylide ions. Let us start with acetylene. If you take a look at acetylene, we told you earlier that this carbon here is an sp carbon. Of course, this is also an sp carbon. Because of that, this hydrogen here is relatively acidic relative to other organic molecules. Okay. For example, if you take a look at this, this hydrogen here, in acetylene, the pKa value, the pKa is about 25. Whereas the pKa for the hydrogen attached to the carbon-carbon double bond is about 40. And the pKa of the hydrogen attached to an sp3 carbon is about 60. So what this tells us is that this hydrogen here is a lot more acidic than all of these other hydrogens here. And therefore, we could take advantage of this by reacting this here, this molecule here, with a base to abstract this hydrogen here and then form a nucleophile. Okay. For example, I could take this. I could take potassium hydroxide. I will get this. Plus water. So it's fairly acidic enough for us to be able to use potassium hydroxide to engage in an acid-base reaction with the acetylene. We could also use, take this out of the way. We could also use sodium amide for the same purpose.
So do you get three products?
Huh?
Do you get three products?
No, you get the acetylide. We call this acetylide ion. This is what we call acetylide ion.
And then it doesn't put in the big plus
And plus water.
So what is the big plus?
No, it's an ion. It's almost like sodium chloride. You have the potassium ion with the acetylide anion, negatively charged and positively charged. Huh? Well, it's like you have any salts, you know, they are bonded together by electrostatic attraction. They are ironically bonded. Just like your table salt. Okay. Now, we could also do the same using sodium amide. Okay, sodium amide is actually a much more powerful base than potassium hydroxide, and you could also get so you get sodium acetylide. Okay, plus of course in this case ammonia. Now you say, what are we going to do with this? What are we going to do with this? We could use this as a nucleophile. You got this? Page 7. Alkylation of acetylide ion. We could take this acetylide ion. You know how we make that now. Take potassium acetylide, for example, and we could take methyl bromide or any alkyl halide. Remember we told you, when I believe this was chapter 2, when we did bond polarity, we said this bond is very polar because bromine is a lot more electronegative than carbon. So it is pulling electron to itself. So therefore, you see here, there would be a partial positive charge on this carbon because of the polarity, the difference in electronegativity between bromine and carbon, and of course this has a partial negative charge. And what that would do is to attract this electron from the acetylide ion. To attract that, this now acts as a nucleophile, attack this carbon here, and in so doing displacing the bromine, and then what do you get? You now have this. Okay? This is very powerful, because this is the first reaction we are going to give you in which we are forming a new carbon-carbon bond. And so we call this alkylation. Okay? We could do the same.
You have to be out right with non-bonding electron.
Yes. Yes. The bromine is here. Okay, it displaces that. That means potassium is still there somewhere. Okay.
So they're both still there?
Yeah, everything is still there in solution. Now, we could also do this There's no limit to what we can do here. We could calculate this. This could react with this. Let me use a different color here. Let me use this here. Okay, we could calculate this so that we now get this. So what have we done? We have extended the carbon chain by 4. We have extended the carbon chain by 4. So this is a very powerful reaction indeed, alkylation of acetylide ion. Okay, before we leave, let us do a couple of problems. My time is my time is expired. Let's see here. Oh, okay, folks. I will see you on Thursday. When we meet on Thursday, there will be a short 7-minute quiz on Thursday based on today's material. Okay.